What is at the center of the Earth? It's a simple question. Kids ask it. We all wonder about it at some point. You dig a hole in the sand at the beach and you imagine just keep going. What would you find? The movies give us ideas, strange worlds, dinosaurs, a land forgotten by time. For a long time, humanity had to rely on imagination. The center of the world was a place of myth and speculation, a place for hell, or a hollow space, or a magical realm. The truth is different. It's less fantasy, but in its own way, much more incredible. The center of the Earth isn't a place you can visit. We will never send a probe there. We will never see it with our own eyes. The pressure is too high, the temperature is too extreme. It's the most inaccessible place we know of, far harder to reach than the most distant planet. And yet we know what's there. We don't know everything. There are still big mysteries. But we have a surprisingly clear picture of the Earth's heart. We figured it out without ever leaving the surface. We did it with cleverness and observation. We used the entire planet as a medical scanner. We listened to its vibrations, we weighed it, we looked at space rocks that fell from the sky. We pieced together a story from clues. So, let's talk about that story. Let's talk about what's really at the center of our world. The simple answer is metal. A giant ball of metal. But that's too simple. It's like saying a person is just water and chemicals. The details are what make it amazing. The center of the Earth is in two parts. There's a core within a core. Think of a peach. You have the skin, the fleshy part, and the pit. But imagine the pit itself had a smaller solid seed inside it. That's a bit like the Earth. We have the crust we live on. Below that is the thick, gooey mantle. And in the very center of the pit is the core. This core is split into an outer core and an inner core. The outer core is a giant churning ocean of liquid metal. It's mostly iron, with a good amount of nickel mixed in. There are probably other lighter elements too, like sulfur, oxygen, or silicon, but we're still working out the exact recipe. This ocean of liquid iron is huge. It's about 1,400 miles thick. The temperatures here are staggering, somewhere between 7,000 and 9,000 degrees Fahrenheit. That's hotter than the surface of the sun. The pressure is millions of times greater than the pressure we feel on the surface. It's so hot that the iron, a strong, solid metal we build things with, flows like water. This flowing, liquid outer core is maybe the most important part of the deep Earth for us. It's the engine that creates Earth's magnetic field. Our planet acts like a giant bar magnet with a north and a south pole. This field extends far out into space, creating a protective bubble called the magnetosphere. This bubble shields us from the solar wind, a constant stream of charged particles blasting out from the sun. Without the magnetic field, that solar wind would strip away our atmosphere over time. It would be devastating for life on Earth. Mars is a good example. It's a rocky planet that used to have a thicker atmosphere and maybe even oceans. But its core cooled down and solidified. Its magnetic field died, and the solar wind slowly blew its atmosphere away, leaving it the cold, barren planet we see today. So that churning ocean of liquid metal deep beneath our feet is the reason we have an atmosphere. It's the reason we're protected from deadly solar radiation. It's a silent, invisible guardian. How does it work? It's a process called a geodynamo. It's complicated, but the basic idea is this. Heat from the deeper inner core causes the liquid iron in the outer core to swirl and churn like water boiling in a pot. These are called convection currents. As this molten metal moves, and because the Earth is spinning, it creates powerful electrical currents. And as we know from basic physics, moving electrical currents generate magnetic fields. It's a self-sustaining process. The motion creates the field, and the field influences the motion. It's an incredibly powerful and dynamic engine room, constantly working at the heart of our planet. It's now for the very center. The final destination, inside that roiling ocean of liquid iron, is the inner core. The inner core is a solid ball of metal. It's about 750 miles in radius, which makes it about 70% the size of our moon. It's also made mostly of an iron-nickel alloy, probably with some other trace elements. The temperature here is even hotter than the outer core. It's estimated to be around 10,000 degrees Fahrenheit, as hot as the sun's surface. This presents a paradox, a question that might pop into your head. If it's even hotter in the inner core than the outer core, why is the inner core solid while the outer core is liquid? The answer is pressure. The pressure at the very center of the Earth is almost impossible to imagine. So it's about 3.6 million times the atmospheric pressure at sea level. This immense crushing pressure forces the iron atoms to pack together so tightly that they can't move around. They are locked into a solid crystal structure. The heat is trying to melt them to make them jiggle apart and flow. But the pressure is so great that it wins the battle. It squeezes the atoms into a solid state, despite the incredible heat. It's a state of matter we can't really replicate on the surface, except for tiny fractions of a second in specialized labs. So you have this solid moon-sized ball of super hot iron and nickel sitting inside a much larger ocean of liquid iron and nickel. It's a truly alien world, but how on earth do we know any of this? It's a great question. We've never drilled more than a few miles into the crust. The deepest hole ever dug, the Kola Super Deep borehole in Russia, only went about 7.5 miles down. The Earth's center is nearly 4,000 miles away, so we're not even scratching the surface. All our knowledge about the core is indirect. It's a brilliant piece of scientific detective work that started centuries ago. The first clue was simple gravity. We were able to calculate the mass of the Earth a long time ago. We did it by observing how its gravity affects things like the moon. And once we knew its mass and its size, we could calculate its average density. It turned out the Earth is very dense. The rocks we find on the surface, like granite and basalt, are not nearly dense enough to account for the Earth's total mass. This meant that the stuff inside must be much, much heavier than surface rock. Something dense had to be hiding in the center. Metal was the obvious candidate. Iron is both very dense and very common in the universe. The next big clue came from space: meteorites. Many meteorites are the shattered remains of ancient planetesimals, small bodies that were forming in the early solar system but never quite made it into full-fledged planets. They got smashed apart by collisions. When we cut these meteorites open, we find that many of them are made of iron and nickel. They are called iron meteorites. The thinking is that these little planets, just like Earth, went through a process called differentiation. When they were young and molten, the heavier elements like iron and nickel sank to the center to form a core. The lighter rocky materials floated to the top to form a mantle and crust, so these iron meteorites are thought to be the exposed cores of these shattered worlds. They are physical samples of what a planetary core is made of, and since Earth formed from the same stuff in the same part of the solar system, it's a very strong clue that our core is also made of iron and nickel. Those were good clues. They pointed to a dense metallic core, but they didn't tell us about the different layers. They didn't tell us that one part was liquid and one part was solid. For that, we needed to find a way to see inside the Earth. And we found one, not with light, but with sound, or rather with seismic waves. Earthquakes are destructive and terrifying, but for geologists, they are also a priceless tool. An earthquake is like a giant bell ringing inside the planet. It sends vibrations, or seismic waves, traveling out in all directions right through the entire Earth. We have sensitive instruments all over the world called seismometers that record these waves. By studying the time it takes for these waves to travel from the earthquake to different stations and the path they take, we can build a picture of the Earth's interior. It's like a planetary scale ultrasound. There are a few different types of seismic waves, but two are particularly important for understanding the core. They are P waves and S waves. P waves are primary waves. They are the fastest. They are compression waves, which means they travel by pushing and pulling the rock in the direction they are moving, like a slinky being pushed from one end. P waves can travel through solids, liquids, and gases. S waves are secondary waves. They are slower. They are shear waves, meaning they move the rock from side to side, perpendicular to the direction the wave is traveling, like a rope being whipped up and down. The crucial thing about S waves is that they can only travel through solids. They cannot travel through liquids or gases. A liquid doesn't have the rigidity to transmit a shearing motion. If you try to shake a rope that's lying in water side to side, the wave just dies out. This one property of S waves is the key that unlocks the core's biggest secret. In the early 1900s, scientists noticed something strange. When a big earthquake happened on one side of the planet, seismometers on the other side would not detect any S waves. There was a huge shadow zone on the opposite side of the Earth where S waves just disappeared. The P waves made it through, although they were bent and slowed down a bit, but the S waves vanished. The only logical conclusion was that the S waves must have encountered a layer of liquid deep inside the Earth that they couldn't pass through. By mapping out this shadow zone, scientists were able to calculate the size of this liquid barrier. This was the discovery of the liquid outer core. It was a stunning achievement, seeing a hidden ocean of metal 2,000 miles beneath the surface just by listening to the echoes of earthquakes. But the story gets even more subtle and interesting. There was also a mystery with the P waves. There was a smaller shadow zone for them too, a region where they were expected but didn't show up. But scientists also found very faint P waves showing up in that shadow zone. It was a puzzle. This puzzle was solved in 1936 by a Danish seismologist named Inge Lehmann. She was meticulously studying the records from an earthquake in New Zealand. She proposed a radical new idea. She suggested that at the very center of the liquid outer core, there was another, smaller core that was solid. She calculated that P waves hitting this solid inner core would be reflected and bent in a way that would send some faint waves into that shadow zone. Her calculations perfectly matched the observations. It was a brilliant deduction. With careful analysis of faint squiggles on paper, Inge Lehmann had discovered the solid inner core. She had found the solid seed inside the stone of the planetary peach, so that's how we know. Gravity and meteorites told us the core was dense and made of metal. Seismic waves, the planet's own ultrasound, showed us its structure, a liquid outer layer and a solid center. But the story doesn't end there. Our tools and understanding have gotten much better since Inge Lehmann's time. We now have global networks of highly sensitive seismometers and supercomputers to analyze the data. And the more we look at the core, the weirder and more complex it seems to be. We are starting to learn some of its finer details. For instance, we've learned that the solid inner core seems to be spinning, and it's spinning slightly faster than the rest of the planet. We figured this out by looking at seismic waves from pairs of identical earthquakes that happened years apart in the same location. The waves that passed through the inner core arrived at their destination a fraction of a second earlier in the later earthquake. Over decades, this difference adds up. The best explanation is that the inner core has rotated slightly relative to the mantle and crust in that time. The difference is tiny, maybe a fraction of a degree per year, but it tells us that the inner core is not rigidly connected to the rest of the Earth. It's floating in the liquid outer core, free to spin at its own pace, likely driven by the same magnetic forces that it helps to generate. Another recent discovery is that the inner core is not a simple, uniform ball of iron. It seems to have its own structure. Some evidence suggests there might be an innermost inner core. By looking at how seismic waves travel through it at different angles, scientists have found that the iron crystals in the very center might be aligned differently from the crystals in the outer part of the inner core. It's like a Russian doll, a core within a core within a core. We're still trying to figure out what this means. It might be a fossil of how the inner core first started to freeze billions of years ago. The inner core is also not a perfect smooth sphere. It seems to have a kind of texture, with some parts where seismic waves travel faster than others. We might have mountains and valleys on its surface, but on an unimaginable scale, where the rock is solid iron and the air is liquid iron. There's also evidence that the inner core is growing lopsidedly. It might be solidifying faster on one side than the other. The whole system is dynamic and complex, not just a simple static ball. And what about the boundary between the core and the layer above it? The mantle. This region, the core-mantle boundary, is one of the most mysterious places on the planet. It's a zone of extreme change. You have the liquid metal of the outer core below, and the hot, but mostly solid rock of the mantle above. The temperature and pressure changes here are enormous. There are probably strange chemical reactions happening. Some scientists think there are huge continent-sized blobs of material at this boundary that are different from the rest of the mantle. There might even be anticontinents of rock sitting on top of the core, or sediments of material that have slowly rained down from the mantle over billions of years. This boundary is likely a very rough and dramatic landscape, and it probably plays a huge role in how heat escapes from the core and drives processes in the mantle, like plate tectonics and a type of volcanism that creates islands like Hawaii. So, why does any of this matter? Why should we care about a ball of metal 4,000 miles away that we can never touch? We've already talked about the most important reason, the magnetic field. Without the churning liquid outer core, we wouldn't have our protective shield. Life on the surface would be impossible. So, the core is directly responsible for our existence. Understanding how it works is critical to understanding our planet's habitability. The heat from the core is also a driving force for our entire planet. The core is like the Earth's engine. While most of the heat comes from the decay of radioactive elements in the mantle, a significant amount of heat flows out of the core. This heat helps to stir the mantle in a process of slow-motion convection. This mantle convection is what moves the tectonic plates on the surface. It's the engine behind earthquakes, volcanoes, the building of mountain ranges, and the opening and closing of oceans. So the shape of our world, the very ground beneath our feet, is shaped by the heat escaping from the heart of the planet. Understanding our core also helps us understand other planets. When we look at planets like Venus, Mars, or Mercury, we can use our knowledge of Earth's core to interpret what we see. Mars lost its magnetic field. Why? Its core is probably smaller and cooled faster. Venus is about the same size as Earth, but it doesn't have a significant magnetic field. Why not? Maybe its core isn't convecting in the same way. By comparing and contrasting these planetary cores, we learn more about the rules that govern how planets form and evolve, and what makes a planet like Earth so special and so suited for life. There is still so much we don't know. Science has given us an incredible picture, but it's still a sketch. The exact composition of the core is a big question. We know it's mostly iron and nickel, but what are those other lighter elements mixed in? Getting the recipe right is important for our models of how the core works. When exactly did the solid inner core start to form? This is a huge debate. The timing of the inner core's birth would have had a massive impact on the magnetic field. Some scientists think it formed relatively early in Earth's history, while others think it's much younger, maybe only a billion years old. Pinning this down would tell us a lot about our planet's past. How will we find the answers? We'll keep listening, we'll build more and better seismometers, creating a finer and finer network to map the deep interior. We'll use supercomputers to create more and more sophisticated models of the core, simulating the physics of liquid metal under extreme conditions. And we'll try to replicate the core in the lab. Scientists use devices called diamond anvil cells to squeeze tiny samples of iron between the tips of two diamonds. They can generate pressures similar to those in the core. Then they can blast the sample with a laser to heat it up. By doing this, they can study how iron behaves under core-like conditions, which helps us to interpret the seismic data we collect. The journey to the center of the Earth is not a physical one. It's a journey of intellect and ingenuity. It's a story about how we can learn about a place we can never go. We started with myth and imagination. We moved to simple observations about gravity and fallen space rocks, and then we learned to listen to the whisper of the planet itself, using the waves from earthquakes to illuminate the darkness. What we found there is not a lost world of dinosaurs, but something just as amazing. A dynamic, layered heart of metal. A liquid ocean generating a life-saving magnetic shield. And at the very center, solid crystal ball iron spinning in the dark, hotter than the sun's surface, a monument to the immense pressure that holds a planet together. It is the engine room of our world, the source of our protection, and a place of deep and enduring mystery. The question what is at the center of the Earth is simple. The answer is anything but. And the best part is we're still listening, still learning, and the story is not over yet.